All right, today we're talking about music and intonation. We have a lot to talk about, so I'm going to try and talk pretty quickly. Hopefully it all makes sense. It's kind of a complicated, one of the more complicated video lectures we're doing this semester, but it is really interesting, so I hope you really get into it. All right, I'm going to use some free software. The first one is called Temperament Studio. It lets you hear the physics of scales. This is free software I wrote. You can download it from this web page. It's in Java, should run on every computer. The other piece is a program called Spectrum Lab, which is a piece of software I found that's really cool. It turns your computer into a spectrum analyzer, and it will show you the different frequencies in a sound. All right? And you can download that from the link given here as well. And if you want to hear more of me talking about intonation and musical scales, I gave a talk at Open West in 2014. You can click on this link and go watch that as well if you're interested. All right, in music there's a lot of definitions, some terms you need to know so you can talk about music the way musicians do. So I'm going to give you a brief glossary here to start with. First of all, pitch. When we say the word pitch, what we really mean is what note are you playing and is that note in tune? The pitch is related to the first harmonic. When you play a guitar string or an organ pipe, you're making lots of different frequencies, but your brain typically hones in on the first harmonic and uses that to decide what note you're playing. There's also the tone of a note, and that's basically how it sounds. That's what makes a trumpet sound different from a guitar. All right? And it turns out the tone is based on all the different harmonics. So your brain hears all these frequencies. It notices that there are harmonics series, so it says, look, this is one instrument playing. It's playing one note determined by the first harmonic, and the other harmonics have to do with how it sounds to you. That's how your brain interprets all these different frequencies. Now there's this thing called an interval, and an interval is just the spacing between notes. All right? If we look at a piano keyboard, it turns out the smallest spacing between notes is what we call a half step. So when I go from this note to this note, that's a half step. From here to here is a half step. From here to here is a half step. And from here to here is a half step. All right? The unison interval is 0 half steps. So the distance between middle C and middle C is unison. All right? All right? If I go up 1 half step, we call that interval a minor second. If I go up 2 half steps, that's a major second. So from here to here is a major second. 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 All right? So the intervals just tell us how many half steps we've taken. All right? Some of the most important intervals are called the major third, which takes us from here to here. It's 1, 2, 3, 4. So 4 half steps is a major third. And a perfect fifth is 1, 2, 3, 4, 5, 6, 7 half steps. So from C to G is a perfect fifth. From G to 1, 2, 3, 4, 5, 6, 7. From G to D, from here to here, is a perfect fifth. All right? Another definition, a chord. A chord is just a group of notes played together. I play more than one string on my guitar. I hold down more than one key on my organ at the same time, and that's a chord. Consonants, if something is consonant, it means that it sounds pleasant. So if I play a chord and the notes sound really good together, I say that's a consonant chord. It has a lot of consonants. Consonance means it makes you want to just sit back and enjoy. Dissonance is the opposite of consonance. If a chord sounds dissonant, it means it sounds edgy or tense. It makes you want to start throwing chairs. All right? And usually what we go for when tuning an instrument is consonance, because if we want dissonance, when do we want dissonance? Dissonance is used a lot in jazz. It builds tension. All right? If we want dissonance, it turns out it's easy to get dissonance. So when I tune an instrument, what I really want to do is get as much consonance as I can. Another term is a just interval. A just interval is an interval involving fundamental frequencies that differ by a ratio of small integers. So for example, if I play 2 notes, and the fundamental frequency of the higher note is 3 halves times the fundamental frequency of the lower note, that's a just interval, because the ratio of those 2 frequencies is just a ratio of small integers, 3 halves. All right? Why just intervals matter will be explained later. But first, I want to point out that we hear pitch logarithmically. Previously, we mentioned that we hear the intensity of sounds logarithmically, but it also turns out that we hear frequency logarithmically. If you plot the frequency of all of the notes on a piano keyboard tuned to equal temperament tuning, Those frequencies as a function of note, they're not linear. It's an exponential curve, all right? We hear pitches logarithmically. What that means is if you ask, how much do you have to go up by an octave? The answer isn't like, I add 100 hertz or I add 1,000 hertz. You don't add something to go up by an interval. You multiply by something to go up an interval. So to go up an octave, for example, you multiply the frequency by a factor of 2. All right, now there are 12 notes in an octave. So if I go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 half steps, I go from one C to another C. I go up to the same note but up an octave. If I start on an F and I go up 12 half steps, I get an F an octave higher. All right? Now, how do you tune an instrument? The equal temperament tuning scheme that we use today splits the octave up into 12 equal parts. So we say the octave's a factor of 2. I want to split that up into 12 equal parts. But what do I mean by 12 equal parts? Right? Remember, we hear frequency logarithmically, which means that going up an interval means multiplying by some factor. So what we do is we say going up a half step means multiplying by a factor of 2 to the 1/12. Going up 2 half steps means I multiply by 2 to the 1/12 and then another 2 to the 1/12, which is 2 to the 2/12, right? Or in general, going up n half steps means multiplying your frequency by 2 to the n 12ths. If you go up 12 half steps, then you've gone up a factor of 2. So equal temperament mathematically splits the octave up into 12 equal steps, each one involving multiplication by a factor of 2 to the 1/12. All right, so we can kind of imagine the notes in an octave kind of like the numbers on a clock face. There's 12 of them, and when you go all the way around, it starts over again, but up an octave. If I go up by a factor of 2 to the 1/12 over and over again, I go and I can calculate the frequency of each note and tune my instrument. All right, that's how equal temperament tuning works. But it turns out equal temperament is not the only way to tune an instrument. It turns out that a long time ago, people used to tune instruments differently. And in fact, although today almost all instruments are tuned to equal temperament, but there are still some people who think that that's not a good idea, that there's better tunings we could use. All right? So there's some controversy. It's not a done deal. So let's talk about one of the oldest ways to tune an instrument, and that's known as Pythagorean tuning, named after Pythagoras. Back in the days of Pythagoras, you could not buy an electronic tuner to help you divide the octave up mathematically into 12 equal steps. But what Pythagoras did is he said, look, we can use the harmonics on a string or on an organ pipe or whatever our instrument is to tune the instrument. All right? The first harmonic tells us the note, right? So I start with some note. I'm going to say, I'm going to define this note to be the root of my scale. Now, how do I get all of the other notes? We're going to use 2 other harmonics. Remember, the second harmonic is twice the frequency of the first harmonic. So if I have some note and I want to tune to some note an octave higher, I can just excite the second harmonic on my first note and then tune my second note, my second organ pipe, my second string to have the same frequency, to have the same pitch as the second harmonic of my first one, and it will be an octave higher. All right? And I can use that by listening to the beating between the sounds, right? So I touch my string halfway from one end, play it, and I hear the second harmonic. Then I play my other string and tune it to get rid of the beats, and now my second string sounds an octave higher than the first one. The other harmonic we're going to use is the third harmonic. The third harmonic has a frequency which is 3 times the fundamental, which means it's 3/2 times higher than the second harmonic. And it turns out a factor of 3/2 sounds like a fifth to you and me. For example, going from a C to a G, 7 half steps. Now this is a slightly different definition of the fifth than what we get for equal temperament. Remember, in equal temperament, the fifth is a factor of 7/12, which is 1.4983. But in Pythagorean tuning, we're going to define the fifth to be a factor of 3/2, which is 1.5. So almost the same, a little bit different. All right? Now using just fifths and octaves, just fifths, technically, this is a just fifth because it's a ratio of small integers. This is not a just fifth. But using just fifths, we can tune and all of the notes on our instrument. And here's how it works. So I start at some note, and I can use the harmonics to find a just fifth, which is 7 half steps higher. So now I can find that note there. I go up 7 more half steps, go a fifth from there, and I get this note here. Well, notice I've already gone past 12, so now I'm an octave higher. If I want to get this note in the lower octave, what do? I use the second harmonic and go down an octave. All right, so it can always go down an octave. Starting here, I go up 7 more half steps, 1 more just fifth, and I get the ninth note. Again and again, doing this over and over again, eventually I can get all of the notes. The next fifth takes me back where I started. Almost. Okay, so people do not usually use Pythagorean tuning today. It's not commonly used. However, guitar players do something sort of similar. I thought this was interesting. If you buy a guitar, probably the frets have been laid out using equal temperament, the common scale we use today. And if you get an electronic tuner to tune your strings, it will be set to equal temperament. But sometimes guitar players, instead of using an electronic tuner, they'll do something called tuning with harmonics. All right? The way you do that is you touch a string at the 5th fret. And it turns out the 5th fret is about a quarter of the way from the nut. So that excites the 4th harmonic. It damps the 1st, 2nd, and 3rd, but you get the 4th harmonic. Then you go up to the next highest string and touch it at the 7th fret, which is about a third of the way from the nut. And that makes you hear the 3rd harmonic. All right? And then you tune the 4th harmonic of the lower string so that it's the same as the 3rd harmonic of the higher string, and you hope that that gets you to the right frequency. And it turns out most of the strings in a guitar differ by a perfect fourth. All right? So does that work out? Well, let's think about this. So what I want is I have some string at some frequency A. I want another string to be at some frequency B, which is a fourth higher, which is 5 half steps. So we want that to be true. And it turns out 2 to the 5/12 is equal to 1.33884, and so forth. All right? But what we're really doing is we're tuning such that the 3rd harmonic of our lower string, right? I said I wanted the 4th harmonic of the lower string. I always do this. We want the 4th harmonic of the lower string to be equal to the 3rd harmonic of the higher string. All right? That means higher string. That means that the higher string will be at a frequency which is 4/3 the lower string. 4/3 is not equal to 2 to the 5/12. We didn't get exactly where we want it to be. 4/3 is 1.3333, and so forth. All right? So it's not exactly the right frequency if we want to do equal temperament tuning, but it's very close. It turns out small differences matter. So which tuning method is best? Is it best to tune an instrument using equal temperament, or is it better to use Pythagorean, or some other tuning method? When I tune my guitar, is it best to use that electronic tuner and get my strings right at the equal temperament frequencies, or is tuning by harmonics maybe better, or is it worse? All right, so it turns out, okay, really the question we're asking is, why do we pretty much always use equal temperament today? And it turns out it's all about consonants. We want to make intervals sound pleasant together. We want chords to sound pleasant. And it turns out that consonants is all about just intervals, because just intervals are all about beating. So a consonant chord is one where we don't hear a lot of beating. So it all comes down to beating. Okay, it turns out we don't hear beating between fundamental frequencies of notes. If I play an A and an E together on an organ, the frequency of the A and the frequency of the E are different enough that although mathematically you can write that as, an average frequency beating together, they're far enough apart that your ear interprets that and it's able to say, no, those are two different notes. So you don't hear the beating, you hear two different notes. All right? It's only when the beat rates are small, less than 50 hertz-ish, that our ear hears it. All right, so where do those beats come from? It turns out they come from the harmonics. When I play an E and an A on an organ, all right, the fundamentals don't beat, but each of those notes comes along with the whole harmonic series. I play one organ pipe, I get a whole bunch of different frequencies. I play one guitar string, I get a whole bunch of different frequencies. And it turns out these different frequencies can beat together. So for example, let's consider the just fifth versus the equal temperament fifth. All right, so for a just fifth, let's say I play a note at some frequency 1. Let's call it frequency A. All right, I'm going to play another note whose fundamental is at some frequency B, And I want it to be a just fifth higher. And remember, a just fifth is a factor of 3/2. All right? Well, it turns out if you look at the frequency of the second harmonic of your lower note, the third harmonic of your lower note, and compare that to the second harmonic of the upper note, what happens? Well, the second harmonic of your upper note, well, your upper note is 3/2 the lower note, all right? And so this turns out to be just 3 times the frequency of the lower note, all right? So it turns out that the third harmonic of the lower note is exactly the same frequency as the second harmonic of the upper note. So the beat frequency is 0. You don't hear beating between those two harmonics, all right? But let's consider equal temperament. For our equal temperament scale, we're going to play some note with some fundamental frequency, but the other note is going to have a fundamental frequency which is 2 to the 7/12 above the lower note, right? An equal temperament fifth is a factor of 7/12. All right, so if I compare the frequency of this note to the frequency of the third harmonic of the lower note to the second harmonic of the upper note, the second harmonic of the upper note is going to be 2 times 2 to the 7/12 times the frequency of the higher note. All right, and 3 is not equal to 2 times 2 to the 7/12. All right, in fact, let's pull up Python here. All right, and let's imagine that I have, what is 2 times 2 to the 7/12? It's 2.996614, so it's not quite a factor of 3, so those two notes won't be exactly the same, all right? So let's do an example. Let's imagine that I play an A at 440 hertz, and then I'm going to play the E, which is a fifth above that. For equal temperament, all right, that note is just going to be a factor of 3/2 above that. So that's going to be, let's not do 440 because the beat rates will be kind of high to here. Let's do 220 hertz. And if I take 220 hertz times 3/2, right, I get my E is going to be 330 hertz, all right? So I'm going to play those two notes together. And if I take the third harmonic of this one, 3 times FA will be at 660 hertz. The second harmonic of FB will also be at 660 hertz, and I won't hear beating, all right? But if I do an equal temperament scale, and I start with an A at 220 hertz, the E, which is 7/2 steps above, which is a fifth above that, that's going to be 220 hertz times 2 to the 7/12, which is 329.63, let's say. So 329.63 hertz. That's what we said it would be. All right? And the beat rate will then be, take that, minus 330. It's going to be, wait, that's not what I want. I want to take 2 times that to find the second harmonic. The second harmonic will be at 659. Subtract that from the third harmonic of the A, and we should get a beat rate at about 0.74 hertz. All right? So 0.74 hertz should be the beating between the third of the lower note and the second of the higher note. All right? So a little bit slower than 1 hertz. All right? We can use Temperament Studio now to hear that. All right? So here's Temperament Studio. We're tuned to equal temperament, and if I play, here I'm going to turn on an advanced feature where I can actually show the frequencies of the notes. So here's A, 220. Here's E, a fifth above that. If we play them together, can you hear the beating? Wow, wow, wow. And it's about at a hertz. It's a little slower than a hertz, just like we predicted. But let's now tune our organ using Pythagorean tuning. Did you hear the change? It's much more solid. You don't hear the beating, it sounds stronger. Now listen as I go back. Equal temperament, Pythagorean. Cool stuff, huh? And I hit the wrong button. There we go. Okay, now let's go back to equal temperament. One of the advanced features here is instead of using the built-in MIDI sounds, I can actually build my organ with by adding sine waves together. So here I've got the first, second, third, fourth, harmonic, and so forth, and how much of each one. So I'm going to play a note here. Here's the organ I built. Can you hear the beating? Watch what happens if I get rid of the third harmonic. There's some other beating going on, but the dominant beating went away. Ah, that higher beating had to do with n equals 4. So you can hear that 0.74 hertz beating. Get rid of the third harmonic in both of the notes, it goes away. Get rid of the second, it goes away. If I go to Pythagorean tuning, it goes away even with those harmonics because the Pythagorean fifth is a just fifth. It involves a ratio of small integers, so harmonics are at the same frequency rather than almost the same frequency. All right? Okay, now I'm going to go to Spectrum Lab. Let's go back to our MIDI tuning so you don't feel like I'm cheating by making my own notes. All right? And I'm going to play my A at 220. And what you see on Spectrum Lab is I get a peak at 220-ish here. I get one at 440 and so forth. All right? So there it is. Maybe I can turn this up a little. If I play my E, I get a peak at 330. At 660 and so forth. I get the harmonic series. If I play them together, they both have a peak at 660. So using Pythagorean tuning, they're right on top of each other. In equal temperament, Spectrum Lab's a little slow, but you can probably see the level goes up and down. Spectrum Lab sees the beating. Now I can change the resolving power of Spectrum Lab, so instead of seeing one note beating, I can make it smart enough to be able to actually resolve the two different frequencies. So let's do that. I'm going to go into FFT settings. I'm going to change this so it has more resolution. And if I zoom in on this, and we find 660 hertz here, now you see it actually sees two slightly different frequencies. One at 660, one at 659.45-ish. That's about where we said it should be, right? So Spectrum Lab tells us everything's working as we expected. All right, so just intervals matter because if you have ratios, if the frequency of one note is a small integer ratio of another note, then these harmonics that almost line up, they don't almost line up, they exactly line up, and the beating goes away, and it makes the note consonant. All right, so we looked at this. So let's think about the Pythagorean scale. It seems like it's a great scale because it's got these just fifths, right? Why don't we use it? Right? And we can go through, we define all the frequencies of these notes by going up in fifths, and this is what we get. So it has a lot of integer ratios, all right? All of the notes are integer ratios. That's great, right? But the problem is you get wolf tones, all right? So all of the fifths differ by a factor of 3/2 except one. So when we tune a Pythagorean scale, we don't really go up 12 fifths. Typically what you do is you go up 6 and down 6. And you end, in both cases, on the F sharp. But going up versus going down gives you two different frequencies. Remember, when we went to our last step, we didn't quite come back to 12. Pythagorean tuning doesn't quite close the octave. All right, so 12 fifths doesn't take you an integer number of octaves exactly. So it turns out there's three halves is not 2 to the 7/12, right? It's just not the right ratio to get you back to an octave after you've gone up a bunch of them. So you get what's known as a wolf tone. So let's take a look at this. If I play a fifth with equal temperament, you can hear the beats, right? If I go to Pythagorean, it sounds very solid. But as I move up, listen to what happens. Those all sound very consonant until we hit the wolf fifth. So there's this one fifth that's different. And while all of the fifths except the wolf fifth are perfectly consonant, they're just ratios, there's one that sounds really, really bad. All right? Some of these ratios are large integer ratios. So the wolf fifth is a very, very large integer ratio. All right? So the Pythagorean scale sounds really good for some chords and some keys, but it sounds really bad in others. All right, it turns out one of the kind of not so great intervals in the Pythagorean scale is the major third, which turns out to be really important. So in Bach's day, they used what they called mean tone scales. In particular, well, a mean tone scale is basically you tune it using Pythagorean tuning, but you intentionally put a little beating into the fifth. So you make the fifth a little bit different than a just fifth. They call that a tempered fifth. And in Bach's day, they used one called quarter comma mean tone, where you tempered the fifth just enough so that the major third was just and it had no beating. All right? But then other intervals sounded bad. So Pythagorean mean tone scales are scales where some chords are perfectly consonant and others are really bad. All right? Ptolemy came up with the Ptolemaic scale, and he said, let's just define each of the notes in my scale to be a small integer ratio of the root. And it turns out the Ptolemaic scale sounds fabulous as long as you only play in one key. All right? So if I tune this to my 5-limit Ptolemaic scale, all right, and if I play a C major chord, it sounds great. Compare this to equal temperament. You hear all the beating? Pythagorean has a just fifth, but not a very good sounding third. Equal temperament's even worse, but Ptolemaic, very solid. But again, watch what happens as we go up in half steps. So, once again, Ptolemy has this great idea, let's make all of the notes just intervals from the root, but by doing that, he made some notes in other notes relative to other roots sound really, really bad. All right, so today, once again, it sounds great in one key, sounds horrible in others. So the idea with equal temperament is we break up the octave mathematically into 12 equal pieces. We never have perfect consonants, right? Except for the octave. The octave is a just ratio, but all others are not just ratios. So we'll never have perfect consonants with equal temperament, but our chords sound equally good, equally bad in all keys. So you can change keys and things don't get horrible. Whereas with other tuning schemes, you can make things sound better for certain chords and certain keys, but worse. And so when Bach wrote music, he was a proponent of making scales more like equal temperament so that you could change keys. But the organs he played on weren't necessarily tuned that way. They were tuned typically to quarter comma mean tone. So there are certain keys Bach just did not write in because they would sound horrible. All right? So what does this mean in real life? Okay, in real life it means if you play an instrument made in Bach's day, music will sound different than an organ tuned using equal temperament. All right. Also, real instruments have dispersion, so everything we say about just intervals is a little bit different. Piano strings in particular tend to have dispersion so that the harmonics aren't exactly an integer times the fundamental, so you have to tune things a little differently. And it turns out pianos are typically not tuned exactly to equal temperament because of the dispersion. And of course, real instruments play music, so the real proof of how good it sounds is not listening to the things we've done today, but listening to like an actual piece of music. So let's load up a piece of music like Pythagorean C minor by Bach. And if you play this in equal temperament, it sounds pretty good. And let's move ahead a little bit. But if you listen to it in quarter comma mean tone, you'll hear it the way Bach intended. Some intervals sound a little consonant, sound a little dissonant, more dissonant than equal temperament, but some sound much more solid than equal temperament. It's kind of a subtle thing. I recommend you go, play with Temperament Studio, listen to this, and you can convince yourself that Bach was able to do some interesting things because he took advantage of quarter comma mean tone. So when you listen to Bach's music tuned on an organ tuned to quarter comma mean tone, there you can kind of see he used some intervals that are particularly bad to build tension and then resolve them with the really consonant ones. You don't hear that on an organ tuned using our modern equal temperament scale. All right, so that's the end. This has already gone on a long time. This has been a fairly long lecture. I'm going to make it even longer because in class we might not have as much time to work sample problems. If you are just totally out of time, you've seen the lecture, you can stop here. But I wanted to give you some sample problems so you kind of had an idea how to work with the things that we learned. So here's our first sample problem. If I tune an organ using equal temperament with the A above middle C being at a frequency of 440 Hertz, so A is at 440 Hertz, what is the frequency of the E, which is a fifth above the A? How do I do that? Well, if you go to the paper I had you read for this section, you'll see perfect fifth, that's 7 half steps, all right? So the E is a fifth, a perfect fifth is 7 half steps, so I'm going to take 440 Hertz, and I'm going to go up 7 half steps, so that's a factor of 2 to the 7/12 because I'm doing equal temperament. And what do I get? 440 times 7/12, so 2 to the 7/12, so 440 times 2 to the 7/12. The answer is 659.255. All right, so finding notes in an equal temperament scale relative to some reference note is just a matter of going up by factors of 2 to the 112. Here's another problem. If I tune an organ using Pythagorean tuning, such that the A is 440 Hertz, now what's the frequency of the E, which is a fifth above the A? Now this is not a Wolf fifth, all right, which means that the frequency using Pythagorean tuning, other than the Wolf fifths, fifths are just a factor of 3 halves higher. So now if I take 440 Hertz times 3 halves, I get 660 Hertz. All right? So if I tuned my organ such that A was 440, if I use equal temperament, the E above that is at 659.3, whereas in the Pythagorean tuning, it's 660 Hertz. All right? So you can use these things we've learned to calculate the frequencies of notes. Now, imagine I'm building a guitar. The distance from the bridge to the nut is 25.5 inches. How far from the nut should I put the first fret? Assume that I'm using equal temperament tuning. All right, so how do I work this problem? I want to know where to put the first fret. So my guitar string has a length L, all right? Which means it has a frequency. What's the frequency of that string when I play it? It's V over lambda. And what's the wavelength of the first harmonic? It's 2L, right? So V over 2L. All right? But I want to go to another frequency. I want to shorten the string to go to some other frequency. Let's call that L prime. So when I push down on the first fret, I want it to go up a half step. All right? So my new frequency is determined by the new length. But what do I want the new frequency to be? I want it to be 1/2 step above the old frequency. So 2 to the 1/12 above F. All right? So if I look at this then, all right, this is what I want F prime to be, but F prime is V over 2L prime. All right? That means what? That L is going to be, if I solve this for L prime, right, multiply and then divide, I'm going to get V over 2 times 2 to the negative 1/12 times 1 over f, right? But what does f equal to? 2 to the negative 1/12. F is just v over 2l, right? So this is going to be 2l over v. The v's cancel, these 2's cancel, and we find then that L prime is just 2 to the negative 1/12 times L. So just a little bit shorter than L, all right? So how far from the nut do I want to put my first fret? Well, I want to shorten the string down to this distance. So how much do I need to change the length of the string? It's going to be L minus L prime, which is L times 1 minus 2 to the negative 1/12, which then is going to be 25.5 inches times 1 minus 2 to the negative 1/12. All right, let's go into Python and we'll say we want our first fret to be at a distance of 25.5 inches times 1 minus 2 to the negative 1/12. And it looks like we should put our first fret 1.43 inches from the end of the nut. So delta L is 1.43 inches. All right, so we've used physics to design a guitar, and that's awesome. All right, one more sample problem for you. Imagine I play a perfect fifth on an organ tuned to equal temperament, and the lower note is an A with a frequency of 220 Hertz. What is the dominant beat rate? All right, we already worked this problem, but let's work it again. So I'm playing an A, and I'm playing a perfect fifth. The lower note is an A, the upper note is the E above it, right? You don't need to know that it's an E. All you need to know is that I have a note at 220 Hertz, and I have another note which is a fifth above that, so it's going to be 220 Hertz times, once again, look at this thing here, a perfect fifth is 7 half steps, so we're going to multiply by 2 to the 7/12. All right? Now, what is the dominant beat rate going to be? Well, we know that a just fifth, right, if we look here, a just fifth is a factor of 3/2, all right? So if this were a factor of 3/2 above that, we would get no beating. So it must be the third harmonic of this note beating with the second harmonic of that note. So we're going to take 3 times 220 Hertz. That's the one frequency. Then the second harmonic of this one is going to be 2 times 220 Hertz times 2 to the 7/12. All right, so we take this note here, go to the second harmonic, and we compare those two. The beat frequency is going to be the absolute value of the difference of those two. So go into Python or your calculator, and we're going to take 3 times 220 minus 2 times 220 times 2 to the raised to the 7/12. And what we get is what we got before, 0.745 to 3 significant digits. All right? And the units are, of course, Hertz. So that is the dominant beat that we will hear, and that's the beat that we heard when we played with Temperament Studio. All right, and so that's the end. Thanks for sticking with it.